Our next speaker is Rajath from ICTP. Who's going to tell us about bosonic and fermionic one-form symmetries and anomaly matching.
Okay, so let me thank all the organizers for all the hard work into organizing this amazing conference, and thank you for the opportunity to speak. So today I'll talk about certain aspects of one-form symmetries. So I'm using the word one-form quite generally in terms of it's some topological line operators in 2 plus 1D, and it could be a non-vertible or invertible line operator. So I'm using the one quite generally. And some aspects about classifying certain one-form symmetries and some aspects of anomaly matching for them. And this is based on work in collaboration with Mahesh Balasubramanian, who is sitting there, and Matthew Buicken. Okay, so the motivation is that one of the reasons why we like symmetries is to study RG flows. So let me consider some UV QFT where you have some group-like symmetry GUV that is preserved by the RG flow, and omega UV is some placeholder for the anomaly of GUV. And if you have an RG flow to some QIR, and suppose GIR is some faithful symmetry of the IR theory, then the GUV symmetry acts on the IR QFT, so there is some map from GUV to GIR. So there's some group homomorphism from the UV group to the IR group. But if you have anomalies for these, then we should have anomaly matching. So an arbitrary group homomorphism is not allowed. We should make sure that these anomalies match, right? So one of the reasons we like non-vertible symmetries is to generalize this picture, where you replace the G's with some B, which are some general non-vertible line operators of the UV theory, and you have some map from now BUV to BIR. So these are some set of line operators, and BUV is some category. So it knows about the lines, their fusion, their anomalies. And you should have some mapping between the category in the UV and the category in the IR. So there should be some anomaly matching conditions. So the idea is that, okay, we should try to identify the non-vertible symmetries in the UV and try to find what is the anomaly matching condition and use that. That will give us more constraints on the IR, right? So there are many works along these lines, both using the SymTFT and without using SymTFTs. But I will not be using SymTFT this time, but I will try to discuss some aspects of within 3 dimensions. Okay, so now we have a kind of a bootstrap problem in front of us. So for groups, any group can be realized as a symmetry of a QFT, and for groups, there is a notion of non-anomalous group-like symmetry. But for rings, these non-vertible line operators, you have to classify them, and when you do the classification, the classification is already involves the anomalies in it, because for some rings are intrinsically anomalous. So there is nothing like sometimes there's nothing like a non-anomalous non-vertical symmetry. For certain rings, like the icing, it's like intrinsically anomalous. So you try to write down some ring and you try to solve some bootstrap equations, including trying to find the FNR, and some pentagon, you solve some pentagon, hexagon, and impose some unitarity. So you try to do the classification of one-form symmetries. And so we have a bootstrap problem. Now, just to set the notation, one quantity that I will emphasize a lot is the spin of the line operators. And another quantity is the S matrix. So I will think about this S matrix as the anomaly, because even in the non-vertible symmetries case, because if you have a set of line operators which are closed under fusion, if this S matrix is non-trivial, then we cannot gauge that entire set of lines. And if the S matrix is completely trivial, we can gauge that entire set of lines, maybe up to a transparent fermion. But so I will basically call the S matrix as the anomaly of the one-form symmetry. And just to remind you that quantum dimension is just the value of this unknot. Okay, so classifying these one-form symmetries is hard. You have to solve all of these constraints. But there are at least 2 cases where we know how to do that. One is a group like this, where the line operators just have a group like fusion, and the anomaly is given by some function on the group. So it has satisfied, it should be a quadratic form on the group, but basically you can classify all the anomalies on the of that one-form symmetry. Another case where you have a classification is when all the spins, all the line operators have spin plus 1. In this case, it is known that any such set of line operators which are closed under fusion and have spin plus 1 is always representations of a group. So it's always like Wilson lines labeled by some representations. So a natural generalization is, what about if you have lines which have spin plus or minus 1. So if the spin is plus 1, I will call it a bosonic one-form symmetry. And if the spin is minus 1, I will call it like a fermionic one-form symmetry. So what if you have a set of lines which are closed under fusion and they have spin plus or minus 1? So this is a natural generalization of this case. So let us look at some examples. One example is the Z2 diagram theory, where you have these line operators here with fusion given by some Z2 times Z2 one-form symmetry, and we know that we have these 3 bosons and 1 fermion in this case. Another example is the 3 fermion model, or spinate at level 1 Chern-Simons theory, where you have 3 fermions on 1 boson. So these two qualify as that kind of symmetries that I'm talking about. And these two are TQFTs. So what is a general TQFT in which all line operators have spin plus or minus 1? So that is the starting point to the full classification. So let us just focus on TQFTs and let us classify all TQFTs where the spin is plus or minus 1. And the claim is that all such TQFTs are just many copies of these two theories. So you don't have anything more. So in particular, any TQFT in which all line operators are plus or minus 1, there are no non-invertible symmetries in those TQFTs. All lines are invertible. So more generally, even in the case of spin TQFTs, or yeah.
Sorry, I'm a bit confused. So if all the spins are plus 1, it's a rep G for some G, no?
But that's not like TQFT.
Okay.
I'm imposing mod.
Okay, you impose non-degeneracy of the pairing.
That's right. So right now I'm talking about classification of TQFTs with this.
Okay, we know about.
I'll come to the general case. Yeah.
Thanks.
Yeah.
Are you assuming it's always unitary?
I am assuming unitarity. Yeah.
You're assuming.
I'm assuming. Yes. Yeah. Yeah. So I'm assuming all the other spherical structure, everything to come along could be fixed by unitarity, and so yeah. So so in the general case, maybe the TQFT is non-unitary, maybe it is spin. You can show that any such TQFT is basically many copies of toric code, many copies of the 3 fermion model, and maybe SVEC. That's the general case you can have. And the proof goes by showing that if the spin is plus or minus 1 in a TQFT, if all spins are plus or minus 1, the quantum dimension of all lines are equal to 1. So that means that all lines must be invertible. And also it uses a classification of abelian TQFTs to write that these are precisely these abelian TQFTs. So I will not go through the proof of this in this talk. I'm happy to discuss this in discussion. It basically uses a part of the F matrix, which is gauge invariant, called the Frobenius-Shor indicator. And you can show this. But I would like to discuss more about the consequences of this. And one consequence is the converse of this. So if all spins are plus or minus 1, then all line operators are invertible. The converse is that if you have line operators with non-invertible fusion, then your system must have line operators with complex spin. So in a setting where if you are thinking about some kind of topological phase where you assume that the low energy is kind of described by a modular tensor category or a supermodular category, the statement is that if you have non-abelian fusion rules, anions with non-abelian fusion rules, the system must have anions with complex spin. So that is a relation between the fusion and spin in this case. So this is the end of my discussion about TQFTs. So please, any questions on TQFTs? Because we would like to understand one-form symmetries in a generic QFT, which is not necessarily a TQFT. The S matrix is not invertible in general. So the question is, how do we classify those symmetries? So let us consider the case of a generic QFT in which you have a set of line operators which forms some set B, and you have some S matrix for it. There are two possibilities. The S matrix is invertible, so then those set of lines form a TQFT. So you are back in the case that we discussed earlier. If the S matrix is not invertible, then there are some transparent lines within that set of operators. So what do I mean by transparent lines? There are some lines for which if you braid it with any other line in the set, you get their quantum dimension. So you can unlink the Hopf link. So you have a set of transparent lines, which I'll call ZB. And this set of transparent lines is a non-anomalous one-form symmetry. You can always gauge that set of transparent lines. So in the TQFT case, you cannot gauge any symmetry without breaking other one-form symmetries. In this case, you can gauge the ZB because it is non-anomalous and it doesn't braid with any other lines in B. So you can always just gauge ZB without breaking any other symmetries in B. So you gauge that part. So ZB is non-anomalous, you gauge it. If you gauge it, the resulting theory has an invertible S matrix because you have removed all the transparent lines by gauging it. And the resulting thing is a MTC or a TQFT. So the resulting thing is one of these TQFTs that we discussed earlier, the E2, F2, and SVEC type. So if you start with a generic set of line operators, the idea is to just gauge away all the transparent lines and you land on one of those TQFTs that we discussed earlier.
If the lines are non-invertible, even if they are transparent, are you sure that you can find this Frobenius algebra, symmetric Frobenius algebra?
Yeah, so if the lines are transparent, the full set of lines which are transparent are guaranteed to be closed under fusion. So it always forms some rep G. Maybe there's a transparent fermion, but I'm assuming there's no transparent.
But then that you can gauge.
Yeah, so then you can gauge it, yes. Okay, but this is kind of a passive definition. I'm saying that if you have such a symmetry, you can always go back to some TQFT. So let me call it some parent TQFT of this symmetry. But we want to construct all such symmetries. So we want to invert this. And we can invert one-form symmetry gauging by doing a zero-form symmetry gauging. So you start with these bosonic and fermionic one-form symmetries. You gauge the transparent lines in it. You go to a TQFT of this type. On the other hand, you can invert it by starting with a G symmetry acting on this kind of TQFT. You gauge, it's a zero-form symmetry now acting on this TQFT. You gauge it, you can construct a bosonic and fermionic one-form, a general bosonic and fermionic one-form symmetry. So this is the correspondence. Now, in this case, when you have a zero-form symmetry gauging, you might worry about all the obstructions. There's an H3 obstruction, H4 obstruction. In this case, you can show that there is no obstruction. There is no S3 obstruction, and H4 obstructions do not matter for the kind of gaugings that we have here. So you can start with your favorite M, you can start with your favorite G, look at some map, and you choose your favorite fractionation class, you can always gauge it, and you will get one of these bosonic and fermionic symmetries. So it's...
What do you mean by H3 obstruction in the absence of the group?
Yeah. I mean this odd. So there is this TQFT and there's a G action on it, and the S3 obstruction vanishes for such an action because it's an abelian TQFT.
So it means that the zero form and the one form symmetry don't form a non-trivial two group.
They don't form. Yeah, I mean there's an action, but there's no Bosniak class.
Okay.
Yeah. So this is how you classify. You start with any of these and you gauge and you get these. So that's the relation. Any questions on this? So basically, you can just use group theory. And if this M was trivial, remember, if this M was trivial, gauging G just gives you rep G here. So that is a special case of where everything is a boson. Okay, so let me go back to the motivation that I had earlier about RG flows. So suppose you have the BUV to be one of these fermionic and bosonic one-form symmetry. It doesn't have to be in this setting, but let us just focus on that. And you have some map from the set of lines in the UV to the set of lines in the IR. And explicitly, you choose some simple line operator X in BUV and map it to some generically non-simple line in the IR. So whenever you do this mapping, in general, it becomes a non-simple line. So this doesn't happen for group-like symmetries. But for non-invertible symmetries in the UV, it can split into a sum of simple lines. Okay? So what are some properties that this map has? So you have a fusion for line operators, and you can fuse the line operators in the UV, or you can go to the IR and fuse them. And the fusion, we expect it to be invariant under RG flow. So we want these integers that show up here to be equal to these integers. So that's that you can fuse. These are topological line operators. You have some fusion rules in the UV, and you have some fusion rules in the IR. So these are line operators after the F map. So you go to the IR and then fuse them. Also, these line operators comes with some junctions. So you have some junction fusion space which counts the number of topological point operators that can exist. So you assume that the RG flow kind of specifies for you a map between these junction spaces. So you have a map between line operators which preserves the fusion coefficients, and the RG flow should also tell you how the junction spaces are mapped to each other. If you have this data, then you can map the FNR matrices of the UV lines to the FNR matrices of the IR lines. So this is the data that you need. So it depends on the RG flow that you have. You have this kind of data which you can use to relate the FNR in the UV to the FNR in the IR. So you can write down explicit formulas for this, but I will not include it here. I will focus on the modular data. But this is the setting. So these are the assumptions that goes into this RG flow. So you get some natural relations from this setting. So you assume the previous slide, then you can derive these very natural conditions that if you have some UV line operator and you go to the IR, the quantum dimensions must match. But in the IR, the line splits into a sum of simple lines. So it's a sum of quantum dimensions in the IR, and the UV, this is the quantum dimension of the UV line operator. So we have these kind of similar expressions in the following context. Like if you have an irrational quantum dimension in the UV, then this relation tells you that the IR cannot be trivially gapped. Because if the IR is trivially gapped, all quantum dimensions in the IR is just integers. You can just take the trivial line and take direct sums of trivial lines. So if there is a root 2, like in the icing, in the UV, the IR cannot be trivially gapped. And we know that these papers already discuss this constraint and how you can rule out trivially gapped phases using just the quantum dimensions. So these papers are on 1 plus 1D, but this relation comes from just the fusion rules. So this relation holds in 1 plus 1D, 2 plus 1D, 3 plus 1D. But once you go to 3 plus 1D, all quantum dimensions are integers, so you don't have these kind of constraints. But in 1 plus 1D and 2 plus 1D, you can use these kind of constraints to say when can you have a trivially gapped phase, when you cannot have it. So that is the constraints coming from relating matching quantum dimensions. But we also have the S matrix. So the S matrix, you can also derive this just from the previous slide on how the FNR matrices are related. You can show that the braiding of X and Y in the UV should be equal to the braiding of SAB. So AB is in the image of these line operators XY. So AB are in IR, XY are in UV. When you have the braiding of X and Y, it should be equal to the braiding of AB, but there's a sum now, because these are non-simple lines in the IR. So if you had invertible line operators, then you will not have the sum. It is just an equality of S matrices. But now you have a line splitting into sum of lines, so you have these sums. So you have these two types of constraints, which comes from both the fusion and the braiding, which you can use to say more and more things about the IR phase. So that's the idea. Questions? Yeah.
Actually, that's your style. So you made the assumption that the map from the UV to IR is braided and monoidal.
Yes.
Is there some justification for the?
Yeah, so the justification is that the fusion and braiding for lines, these are topological lines, so it shouldn't depend on the scale. So it doesn't matter, where because this BUV is something that is preserved under the RG flow. So these remain as topological operators along the entire RG flow. So the justification is that even though some lines might become trivial, so some lines may be mapped to the trivial line in the IR, or it may split into some lines in the IR, the braiding and fusion should be respected. So that's the input.
So you're assuming that the one-form symmetries in the UV are also topological. Mm-hmm. Because I thought that you were introducing these transparent lines in the UV that are not topological.
They are topological, They are still topological. They are symmetries of a QFT. So they are transparent to other topological lines that I'm considering, but they are not transparent to other non-topological degrees of freedom in my QFT. So they still act on something. It's just that within the class of topological lines that I'm considering, they are transparent. So this doesn't happen in topological phases or TQFTs. But when you study QFTs, you can have rep G, like this Wilson lines, right? Rep G, which is completely transparent to each other, and it can be a sector of topological lines in a more complicated QFT.
But then I'm a bit confused because I thought that then it would be a gapless theory.
Yeah, it could be. It could be. Yeah, I'm not assuming anything about that in this discussion. Yeah, and in this case, I am allowing the IR to be gapless also. It could be a gapless phase. I'm just keeping track of the line operators along the RG flow. If the IR is gapped, for example, then the IR categories must be modular tensor categories. So then in the IR, you should not have transparent lines. Yeah, that is true.
Okay.
Yes.
Just to understand the context, can you give me a concrete example of a dynamical QFT that has some non-abelian anyons, but is not just the stacking of a dynamical QFT with a TQFT or a topological manipulation of this?
I will be discussing an example, but that will be a topological manipulation or a stacking in a way.
Okay.
Yes, but yeah, I think to understand some aspects of this, that example serves the purpose, but yeah. It's not a more complicated example than that. So let me go to that example, which is a simple toy model where you just stack the toric code on a scalar field. You just consider some scalar field and you have the toric code. And the toric code has the EM duality, which permutes the two lines. So there's a Z2 zero form symmetry. And the scalar field also has a Z2 zero form symmetry. And you consider the diagonal Z2 that acts on both. And then you gauge it. So when you gauge this diagonal, you couple these theories, and what are the set of lines that you get once you gauge? So you gauge this Z2 symmetry, then you get the following lines. So I'm just labeling them 1 plus 1 minus because these come from the trivial line. Then we have the psi plus psi minus, which come from this fermionic line in the toric code, and you have one E and M, an orbit of E and M, because E and M are mapped to each other, so you get a non-vertible symmetry. And all of these have spin plus or minus 1. So this is actually a Z2 times Z2 Tambari-Yamagami category, which is this BUV in my setting. So this is the UV theory. And this is a category in which all lines are plus or minus 1. And this is not an MTC because this 1 minus is a transparent line. It's transparent to everything else. So it is something which has transparent lines in it. And it is Z2 times Z2 Tambari-Yamagami category with some braiding on it. So this is the setting. Now you do a very simple RG flow where you take the mass, you introduce mass and take the mass to infinity, and this is like forgetting about the scalar field, and then the IR is Ising times Ising bar. Because when you gauge a Z2 symmetry of toric code without a scalar field, you get Ising times Ising bar. And that is what basically happens when you put a mass to the scalar field. So, but in this case, what happened is that the BUVs was a set of symmetries which did not have complex spins. It was some line operators with plus or minus 1 spin. And in the IR, you necessarily have, in this case, a line operator with complex spin, multiple line operators with complex spins. So you got some TQFT in the IR in which the emergent symmetries have complex spin. So, and more mathematically, this is some modular extension of the IR, the UV category that you started with. So whenever you can start with the BUV, which is not modular, and whenever the IR is gapped, it should be a modular extension of the image of that category in the IR.
What was the role of the scalar field in this construction?
Yeah.
It's the same thing without the scalar field. What would be different?
Yes, so the reason why I introduced scalar field is that because the scalar field is charged, it has transforms under the Z2, this 1 minus Wilson line can end on the scalar field when I gauge the Z2. So there are some lines which become non-topological just because of the presence of this scalar field. If I didn't have the scalar field and gauge a Z2 symmetry of toric code, I will get Ising times Ising bar as the outcome. So there are some twisted sector lines that are coming, but because of the scalar field, they are non-topological.
Question here. So there are more than Ising bar. There are also other versions of Ising. Why you didn't get those one? Why you get?
Yeah, so it depends on the precise way in which I gauge this. I did not. Yeah, so I wanted to do a gauging in which I get Ising times Ising bar. Yeah. Okay. So let me conclude by saying that we have certain TQFTs in which we can consider TQFTs in which the line operators have spin plus or minus 1. They are all abelian. And using that fact, you can classify all possible one-form symmetries where the spins are plus or minus 1. In fact, you can even classify the all possible braidings on such categories, because all of that is determined by this simple classification of TQFTs. And you can consider RG flows where there are some results which I haven't mentioned here, but you can derive sufficient conditions for the emergence of complex spin in the IR. So even if you start with the BUV, which has only real spins, you can determine some sufficient conditions where the IR must have, if the IR is gapped, it must have complex spins. So there are many operant problems. One is of course, to study more non-trivial RG flows, apply this to settings which are much more non-trivial, and understand what are the constraints you can get from these general expressions relating quantum dimensions and braiding. And another one is you're in 2 plus 1D, so you should really include the surface operators in the setting. So you have lines and surfaces give us more anomalies, mixed anomaly between lines and surfaces, or self-anomaly of the surfaces. So really the construction you have must be some BUV in which you have both lines and surfaces, and a BIR which has both lines and surfaces, and study RG flows in that setting. So that's also an interesting problem to study. Okay, thank you.
So this category theory, BUV, why has to be unitary?
Yeah, I'm assuming that the UV QFT is unitary, and I'm thinking that a category within that is unitary, because then the fusion spaces are assumed to be some Hilbert spaces, and I'm assuming that the fusion matrices are unitary matrices.
The thing about unitary, it depends on a spherical structure. There's nothing in your UV theory can choose a spherical structure at all.
So I'm kind of trying to go the other way, where I assume that it is unitary, then the spherical structure is fixed. Yeah, I'm assuming unitarity. Yeah.
About the particular example that I described, am I understanding correctly that the additional topological defect of fractional spin comes from the Z2 monogamy line along the RG flow?
From the Z2?
So in the scalar field theory, after you implement the Z2 gauging, there's non-topological line defect, right. The Z2 monogamy line, like in 2 dimensions, the vertex operator, and in 3 dimensions, the line operator.
Right.
Does that line become the additional topological line of fractional spin?
That's my expectation, yeah. Those are the ones which become topological, yeah.
It'll be interesting to see how the fractional spin arise by studying that monogamy line.
Yeah, definitely, yes.
And I think that related to Nat's comment, I think you can run this procedure for any Z2 symmetric quantum field theory. You can do the Z2 gauging and you have the monogamy line.
Right, exactly, yeah.
If there's no further questions, let's thank the speaker again.